Hi everyone, we are the Spartan Superway Boogie Chassis Team, and this is our team. Andrew will start it off with implementation of rapid transport networks.
The Spartan Superway Project is a rapid transport network that plans to revamp the public transportation system to fit our modern time. The way the Spartan Superway Project plans to accomplish this is by implementing various new features to the transportation system. Imagine the bus transit system in a city, except instead of buses, there are independent pods suspended in the air that are autonomously controlled and powered by renewable energy from solar panels. This is exactly what the picture on the left is aiming to show. Rapid transport networks have been implemented in some cities, proving to be convenient as well as cost-effective. We can take a look back at a system that has shown success for over 25 years, such as the one at West Virginia University pictured on the right. The WVU Rapid Transport Network has been used over 83 million times and only charges non-student users 50 cents. The personal pods are also powered by electrical motors and constantly monitored through computers, similar to what the Spartan Superway aims to do. Some key takeaways that make the Spartan Superway Autonomous Transport Network special are characteristics such as offline stations, which can be used at times that are convenient for users in order to accommodate for all people. Non-stop, allowing easy, quick, and convenient trips for busy citizens. Always on demand, making sure that a pod is available for any consumer to use in order for them to travel with little to no wait at any time of the day. Solar powered. Being powered electrically has many benefits relating to the environment. Exclusive guideways, ensuring a familiar and solo path that the pods will travel on. These traits of the Spartan Superway Project can be vital for our modern times that we live in today. The Spartan Superway Project consists of 4 teams: Switcharm, Track, IoT, and Boogie Chassis. The Boogie Chassis specifically, however, holds a high importance and is vital in many various industries. The chassis' role is to be the main support system of a vehicle. It should also be able to withstand the vibrations and forces in dynamic condition. The picture on the left is a chassis that is used for trains, in which is needed to operate for extreme long conditions. If the chassis has issues or doesn't work, the train simply won't move. As you can see, the chassis is essentially the skeleton of the vehicle, which gives way to the importance of our role as a Boogie Chassis Team. The role of the Boogie Chassis Team is an integral part for the project. We serve as the base of the movable pod, as seen on the right picture. And because there are a lot of specifications and dependencies that teams need from us and we need from them, our project is even that much more important. This will be talked about later in the presentation. Our particular project is to create a Boogie chassis that carries its energy supply and operates under wireless control while withstanding a designated load on the 10-meter scale model guideway. More specific tasks can be divided up into 4 different categories, such as mechanical design, sensors, power systems, and suspension. To achieve this goal that the Boogie team has, it is important that all the teams can integrate together smoothly to ensure the project as a whole goes soundly. Now, I will hand it off to Christian to introduce the mechanical team slides.
We will now get into the progress that we've made on the mechanical team. Manufacturing is a major dependency for the Boogie and Chassis team. We want to ensure that anything we design is realistically attainable, considering the limitations of the manufacturing equipment that we have available to us. A majority of our manufacturing and prototyping will be done utilizing the machining equipment in the student machine shop, as well as the 3D printers in the Spartan Superway Design Center. We are currently waiting on confirmation regarding access to the SJSU Central Shop, as this would grant us access to the CNC machining equipment as well as the water jet. As we move forward from the development phase and into the prototyping and testing phases, we will utilize the versatility of 3D printing and leverage its capabilities to get a better grasp on how our design actually interfaces with other components of the system, i.e. the track, switch arm, electrical components, and the cabin. This is extremely useful as we'll be able to try out various prints and designs and solutions in a short amount of time, and material consumption is generally more cost-effective than using metals to prototype. Lastly, 3D printing will also help us reduce the overall weight of the Boogie by enabling us to print out any components where metal is deemed unnecessary. Up next is Max, and he will be discussing design objectives, specifications, and challenges to overcome.
It is expected that problems will arise during the design process, and specifications need to be created and implemented in order to solve these problems. First, the chassis must have the strength to support applied loads due to passengers, carriage, and traversing turns in the guideway. A suspension system needs to be implemented to minimize the rocking and vibrations from track irregularities and going around turns. A 100-pound load will be applied to the bottom of the bogie to represent the passengers and carriage at this scale. The chassis needs to be compatible with the existing 10-meter track. To fit the current track, the bogie will have 4 wheels resting on the top of the guideway and another 4 wheels tilted 90 degrees to prevent lateral movement. The existing railway gauge has a tolerance of plus or minus quarter inch, thus the top wheels must have a 6.5 inch gap between them. In addition, the inner guide wheels must fit within a 6-inch envelope. In order to consider the bogie functional, it must also be able to navigate autonomously across the guideway using the data collected by the various sensors throughout the Superway system. The bogie needs to be able to start and stop moving at a smooth pace for passengers, and we will be designing it capable of accelerating up to 12 miles an hour in 10 seconds. The bogie also needs to come to a complete stop at charging stations, close enough to wirelessly induce charge back into the battery. The battery will need to be sufficient to power all electrical equipment on board the bogie. The bogie system will also need to have obstacle detection, which will stop the bogie rapidly within 6 inches in case of unexpected interference on the guideway. In order for quick processes such as this, data collected must be transmitted to IoT within a maximum of 5 milliseconds. Next, I'll let Michael talk about our design process.
During the brainstorming phase, we used a traditional chassis similar to the center picture on the slide, and we attempted to modify it with electrical components. One obstacle for design was suspension. The current design has taken inspiration from the first image for testing. The far right image on the slide was an early concept sketch showing components desired, such as cable management housing, switch arm platform, carriage attachment, and attachments for lateral wheel supports. Next, Max, Carlos, and I will introduce the progress we've made on the chassis.
The design on the left shows one of the initial designs for our chassis. We immediately knew we needed a lot of space to integrate all the components of the system. This led us to the 2-level design. The idea is electrical elements go on the lower level, and the entire top level is left for the switch mechanism. Because the chassis for Superway functions similarly to train cars, they inspired the design of the suspension system, but the design lacks an efficient way to connect axles to the chassis, as well as uses an excessive amount of material. This leads us into our second design.
Alternatively, the secondary design focuses on a smaller footprint with more experimental ideas and concepts for implementation. Next is Carlos with the current concept.
Finally, the current design is a larger model intended to fit most of the components in a single surface. Michael will further expand on the secondary concept.
Alongside the development of the main bogie chassis is our experimental second design. For the secondary design, the design philosophy is to create a bogie chassis with a smaller footprint. Additionally, we wanted to emphasize modularity with attachable components to the chassis. These components include the cable management housing, switch arm cover, lateral wheel support, and pseudo-carriage attachment. Compared to the current design, the length and width are significantly shorter. In order to accommodate for the dimension constraints of the switch arm, we created a switch arm platform that doubles as a lid for cable management housing. The only downside to this design is that it does not have a suspension system. Next, Carlos will go more in depth on the current design.
The max dimensions on the bogie are labeled in the image. It can be seen that the bogie has a max dimension of 16.83 inches in length, a max dimension of 3.97 inches in height, and a max dimension of 12.75 inches in width. The 7.7 inch by 11.36 inch dimensions pertain to the area where the components will be located. The dimensions are subject to change given if any new constraints appear when integrating with other systems, such as the track and switch arm. One thing that won't change are the main components that make up the bogie. The main components incorporated into the bogie design consist of the main bogie frame that will contain all the electrical components, such as the sensors and power system, in addition to the switch arm. Second, we have an axle that is fixed to the bogie chassis by an axle clamp, hinge, and dowel pin that will allow the components to rotate as the bogie oscillates. Then we have lateral stabilizer wheels that will maintain the bogie on the track and restricted to shift laterally, which will be mounted using ⅛ bolts and wing nuts for easy installation. The suspension system is comprised of the suspension link and springs to counteract the vibrations acting on our bogie. The suspension is connected to the Maytech hub motors using 3/8/16 washers and cap nuts. The main components on the bogie can be clearly seen in the animation. In order to demonstrate how precisely all the components fit together, an exploding view of the bogie was performed. This is how the bogie will be intended to be assembled and disassembled. For the first step, the cap nuts are unscrewed to enable the removal of the suspension system. Second, as the suspension is removed, the hub motors can be removed from the axle. Third, the lateral stabilizer wheels can be removed by unscrewing the wing nuts from the bolt. Lastly, the axle can be removed by moving the dowel pins from the hinge. Using Abacus, the finite element analysis for the aluminum chassis was performed to simulate a distributed load of 100 pounds at 3 inches from the center of the bottom surface. It was determined through the simulation that most of the amount of stress will be located at the corners of the extrusions with a max von Mises stress of 274.1 psi. In order to decrease the amount of stress at the location, fillets will be added to avoid stress concentrations at the sharp corners, given that the circular shapes are stronger and are more resistant to deformation. Next, Devin will develop more on the electrical side of the bogie.
For the brains of the operation, we will use a Lolin D32, which has an ESP32 chip with Wi-Fi capabilities. It features 3.3 volt operating voltage, 22 digital I/O pins, 6 analog input pins, and 2 analog output. It supports I2C, SPI, and UART communication. We will use UART to talk to motors and SPI for collecting data from sensors. The data will then be sent as JSON files to IoT through Wi-Fi. Next, Hussein will go over power distribution.
Thanks. This is a general overview of how the power distribution board is going to be designed. The ESC and power distribution board get a direct connection from the battery. The power distribution board is a circuit that dissipates electrical energy throughout the system. This includes the sensors on the bogie, which consists of a LiDAR, an inertial measurement unit, and a Lolin D32 microcontroller, the switch arm stepper motor, and microcontroller as well. There are 2 solutions to monitor the state of charge of our battery. The first solution is using Coulomb counting, also known as current integration method, which calculates the SOC by measuring the battery current and integrating it in time. This method is easy but suffers on a long-term basis due to the lack of an updating reference point, such as by resetting the SOC to 100% when a charger determines that the battery is fully charged. The second option is using a Kalman filter to predict the overvoltage due to current and combining it with the Coulomb counting, which provides a much more accurate reading, although this process is much more complex and is a contingency plan. The next slide, we talk about how there's just going to be one battery on the bogie that powers all the different components comprised in it. The reason LiPo was chosen is mainly because of its efficient cycle and higher energy density, power density, as well as the nominal voltage. The maximum current draw for the battery is going to be 11 amps, which will be for the motors to move the bogie with the weight defined. The motors can handle 11 amp of current on 22.2 voltage input without an issue. A battery with the capacity of 5,000 milliamp hour when discharged at 2.2 C can easily produce 11 amps of current and hence allow the bogie to function for around 0.4 hours on a single charge. The other components of the bogie need either 3.3 volts or 5 volts and minuscule current compared to the motors. Therefore, the battery sizing needs to only take into account the motor parameters. Next, we have Alex, who will talk about the brushless DC motors and the ESC.
A 3-phase brushless DC motor is required because we think it has less overall maintenance, has a high output compared to its size, and superior thermal management compared to brushed DC motors. The 3-phase also generates a high resolution and is more energy efficient than a single-phase motor. Encoders are required to tell us the acceleration and velocity to verify the speeds of the bogie during employment. Ability to drive the motors at different speeds is required to account for differentials during turns, since a gearbox will be too bulky for the bogie's design. So we need a high torque brushless motor with 3 phases that has a built-in encoder. So we picked the Maytech brushless 70mm motor and Flipsky speed controller to meet our specs. The brushless motor has a kV of 60. That means that it has a fairly high torque given its size. The Flipsky is small, lightweight, and supports UART communication. It's rated for the battery and has a max voltage spike of 60 volts, so it's well within range to protect the motor itself. Now we'll discuss how the Maytech motor is verified. The Maytech motor is verified using the kV value. A rough equation is used that calculates torque, comparing it to the input amperage and the kV. Torque can also be determined by using dynamics, and then we can verify that the torque required to move a 68 kilogram mass from 0 to 15 meters per second in 10 seconds is 1.5225. For reference, the 68 kilogram mass and the Vmax are both well over our scope that we anticipate the bogie to actually move at, as we want to give the motor plenty of leeway. So we found that we only need 11 amps to meet this criteria, which means that we should be well within our range for the actual final design. For the code base for the motors, we'll be coding in C++. We're using given libraries for the VSC, and we're going to be packaging it in JSON files. The JSON files will be then sent to IoT. Next, we'll be coding the motors to ensure that we do the differential gear drive to better bank the curves for the actual motors. Next, we'll be passing off to Devin to discuss the IMU.
The purpose of the IMU is to measure bogie tilt and acceleration. We will use the board to ensure that the bogie does not exceed 5 degrees of tilt or half a G of acceleration around corners. We chose the LSM9DS1 board for its low cost and functional specs. It accepts an input voltage of 3 to 5 volts, which works well with the Lolin D32. This board is small, lightweight, weighing only a couple grams with a size of 1 inch by 0.7 inches. Its resolution is 16 bits and has both I2C and SPI serial communication capabilities. For our applications, speed is very important, so our team will use SPI as it is faster than I2C. We will also implement a complementary filter for the IMU. The IMU consists of a gyroscope and an accelerometer. The gyroscope is faster, but is also prone to drift over time. The accelerometer isn't prone to drift and is more accurate, however, is slower. A complementary filter will be a compromise and take data from both the accelerometer and gyroscope to get a happy medium between speed and accuracy. Next, Jake will talk about object avoidance.
When designing the obstacle avoidance system, we evaluated a few different sensor options. We initially looked at line of sight sensors, specifically Sonar. The main benefits of Sonar were the small, lightweight build and the budget-friendly cost of $5. Unfortunately, Sonar in this implementation is not very precise and did not have a viable field of view to account for turns in the track. We also looked at using a camera with machine learning. The benefits of the camera are that it has a wide field of view, can be used with existing machine learning software, and some implementations have their own processor. We decided against using the camera because it would have been time intensive to implement and there would be issues aliasing data. We eventually landed on using a 2D LiDAR system in the form of the Slamtech RP LiDAR A1. This system has a 360-degree view and is more accurate than any of the previous systems. The A1 has a maximum range of 6 meters and a minimum range of 0.15 meters. The resolution is either less than 1% of the distance the light travels or less than 0.5 millimeters. As you can see in the diagram, the LiDAR enables us to see in a 360-degree field of view. Our plan is to use the LiDAR for two different purposes. First and foremost, we will implement an object avoidance system using LiDAR. The object avoidance system will detect any obstructions on the track, such as the stuck bogie. Second, we will determine the location of the bogie on the track. Our first implementation of the LiDAR will be based off a state comparison. We will use the map that we generated of the track, then compare the map to the state with their current state. Using our algorithm, we will determine what constitutes a state being out of alignment. If the state is out of alignment, we will stop the bogie. The first implementation relies heavily on a separate system that will let us know the bogie's location on the track. Our second implementation will use simultaneous localization and mapping, or SLAM. SLAM will use pre-generated maps of the room to determine the bogey's location. Slim effectively cuts out the dependence on any other team for knowing the location of the bogie. To power the algorithms we will use for LiDAR, we chose the Raspberry Pi Zero. Most algorithms that are used to implement SLAM rely more on RAM than CPU power. For that reason, we decided to start with the Raspberry Pi Zero instead of a CircuitPython board. Pi Zero should have enough CPU power and RAM to run the algorithm. Next, I'm going to pass it off to Alex to talk about dependencies and contingencies.
Being the bogie team, we have a couple dependency contingencies since we are so core to the rest of the development. For the switch arm, we need the total weight of the switch arm system in order to validate our final motor. The way our contingency around this is essentially just making sure our motor is well above spec, so it can handle a stronger mass than we ever expect any single team to have. For the switch arm electrical system, we're waiting on the final sensors, boards, and motors to ensure that our power distribution board accurately and correctly gives it the power it requires. If that does not come through, then we're just going to ensure there's extra space for an external battery so switch arm can do all of its stuff on its own. We are also waiting on the track team's final sensor, if there is one, to go on the bogie to also implement into our power distribution board. If that does not come through, then we're just going to make the track team sensor fairly modular, give it a simple 3-pin connector. For the charging station, we need to be in collaboration with TrackArm to figure out what the best way of approaching that is going to be. If that doesn't come all the way through, then you're going to have the battery housing be modular, so the battery can be charged by just removing it from the bogie itself. Finally, we're waiting on IoT's MQTT protocol, so a walkthrough of how to send data to IoT. If that doesn't come through, then we'll have all computation performed internally on the bogie itself.
This is the current team Gantt chart. Based on the number of completed tasks, we are still expected to finish on time. Next, I'll go more in depth on the progress of the mechanical team. During the time of this presentation, these are some tasks we have completed and are working towards. On the mechanical team, we are collectively on track with the CAD design of the bogie chassis. As we approach the end of October to early November, we will have an official design that will be reviewed for further analysis and testing. We're currently in the middle of completing the final solid model. For simulation and testing, we're using the program Abacus. However, we might use SolidWorks FEA in combination with Abacus for more conclusive results. For suspension, we are slightly behind in terms of implementation due to designing all the other components involving the bogie chassis. To deal with the delay, we'll be delegating 2 of the mechanical members to get a head start on implementing a more robust design of the current suspension system. Next will be Devin on the progress with electrical.
Currently, the electrical team is making good progress. Motor sizing, battery sizing, and sensor selection is all done. Currently, the programming for the ESC, IMU, and proximity sensor are being worked on. There has been success with getting the microcontroller to communicate with the motors. As we go into November, our main focus is finishing the software for IMU and ESC. The power distribution board should be started as well as the proximity sensor. Progress on proximity and power distribution will be made throughout next semester. This concludes our presentation. We will now take any questions.